Whatever you do, trust your instruments. It's the golden rule for every pilot, drilled into their minds from day one of flight training. But what happens when that very trust becomes the problem? What if the instruments are lying, and the pilot doesn't realize it in time? Would anyone dare to question them? And what happens if they do? November 14th, 1990. Milan Linate Airport, northern Italy. The weather was gloomy, with a blanket of cloud hanging low over the tarmac. Two Alitalia pilots stepped out of their taxi and walked into the terminal of Milan's recently renovated second airport. These weren't strangers. They had flown together the day before and were scheduled for 4 more legs that afternoon and evening. By 1300 local time, they had settled into the crew room, reviewing weather reports, NOTAMs, and flight plans. Their aircraft, a sleek, silver McDonnell Douglas DC-9, 16 years old, but still cutting a sharp figure, was already waiting outside on the apron. The first leg would take them from Milan to Frankfurt, followed by a return flight, then 2 shorter hops to and from Zurich. If all went well, it would be a relatively short and standard day. The weather across the Alps wasn't ideal. Low clouds, scattered rain showers, and light westerly winds. But visibility was generally acceptable. Only one concern stood out: the possibility of fog forming on the final leg. For experienced pilots, fog is never just fog. It can quickly turn into a trap, especially when flying precision approaches in marginal conditions. After briefing their 4 cabin crew members, the pilots proceeded to the aircraft. The captain, a 47-year-old Italian with over 10,200 flight hours, had a solid background. He began his flying career in the military before joining Alitalia, gaining experience on the DC-8, DC-9, and Boeing 727. He had logged over 3,200 hours on the DC-9, though only about 1/200 of those as captain. His first officer, on the other hand, was just 28 years old, with a total flight time of only 831 hours. A recent graduate of Alitalia's Flight Academy, he had entered the cockpit just a few months prior. This stark contrast in experience created what's known in aviation psychology as a steep authority gradient. It means the first officer may hesitate to challenge the captain, even when noticing something is off. A dynamic that has played a key role in multiple past accidents, including Tenerife in 1977 and Asiana 214 in 2013. Once inside the cockpit, the captain opened the technical log and found 2 recent entries that raised concern. The first noted that VHF NAV2, when selected in position 2, failed to provide proper to/from indications on HSI-2 during an ILS approach. The second was more troubling. During a simulated CAT-2 approach at 200 feet, the autopilot deviated below the glide slope, corrected itself, then abruptly dived, forcing the crew to disconnect it and fly manually. These are not minor squawks. The ability of an autopilot to correctly fly the glide slope during low visibility landings is critical. A malfunction like this during a real CAT-2 approach, where visibility can be as low as 100 feet, could have catastrophic results. Ground engineers at Line 8 tried to isolate the problem by swapping the nav radio receivers to see if the issue followed the hardware. After their tests, they allowed the aircraft to dispatch, but downgraded it to CAT-I approaches only. While technically permissible under MEL, minimum equipment list provisions, this decision blurred the line between redundancy and risk. The DC-9 has dual nav radios for a reason, and even with CAT-I, system integrity matters. Despite the issues, the aircraft was otherwise cleared for flight. The crew completed their setup and departed at 14:07 for Frankfurt. No significant anomalies were reported during that leg, though a minor ground floodlight had to be replaced during turnaround. But on the return to Milan, the same navigation issue reappeared. This time, not with NAV2, but with NAV1. This shift in failure source was deeply concerning. If the fault had moved from one radio to the other, It suggested a deeper systemic issue, not the radios themselves, but perhaps the logic of the switching system or the indicators. In a cockpit reliant on accurate instrument readouts, uncertainty like this can be deadly. To fully understand the implications, we need to look at how the DC-9's navigation system works. The aircraft is equipped with two VHF nav radios, each capable of tuning into VOR or ILS frequencies. The flight crew can select which radio feeds which instrument, usually using a selector switch to route NAV1 or NAV2 data to their respective HSIs. But when that switching system or its indicators malfunction, the pilot might see what looks like a valid signal, only it's false. And that false sense of security can become lethal during instrument approaches. This is eerily similar to the 1996 crash of Bergen Air Flight 301, where faulty airspeed readings from a blocked pitot tube caused the pilots to trust incorrect information. That misplaced trust spiraled into confusion and ultimately tragedy. The lesson? When bad data looks good, it's far more dangerous than obvious failure. And so, by the time the aircraft launched for its third leg, this time with the less experienced first officer at the controls, the scene was already set. The instruments were sending conflicting signals, and no one truly understood why. What came next would push the boundaries of trust, training, and cockpit coordination. The navigation radios on the DC-9 are the pilot's eyes when the sky turns gray. They're designed to receive signals from VOR beacons, omnidirectional radio transmitters that send out radials, or bearings, covering all 360 degrees of a circle. Pilots use these to determine their position relative to the beacon by matching their course selector on the HSI, the horizontal situation indicator, to a specific radial. But position alone isn't enough. You also need to know your direction. The aircraft can be on the same radial, whether it's heading toward the beacon or away from it. That's where the to from indicator becomes essential. And that's exactly what had been malfunctioning for both the previous flight crew and now this one. A missing or incorrect to from indication means one critical thing. You can no longer trust what the instruments are telling you. These same nav radios are also used for ILS approaches, instrument landing systems that guide the aircraft precisely down to the runway, both laterally with a localizer and vertically with a glide slope. Precision is everything here. At low visibility, pilots rely completely on these signals to land safely. Now, enter the nav switching unit, the overlooked brain of the whole system. This box determines which nav radio feeds the instrument displays. When set to Radio 1, it sends NAV1 data to both pilots' HSIs and ADIs, automatic direction indicators. When set to Radio 2, it switches everything over to NAV2. But when set to Approach, it splits the system. The captain receives data from NAV1, and the first officer gets data from NAV2. That split is deliberate. It's a safety feature, designed to help the crew detect anomalies by comparing two independent signal sources. If the captain's instruments show a stable glide slope, but the first officer sees an erratic one, they'll know something is off. But this only works if the system is doing what it's supposed to do. And here's where things get even more complex. These nav radios also included a fault monitoring function, an early safety system that helped analog instruments detect when something had gone wrong. If a nav receiver detected an internal error or signal loss, it would trigger a fail flag on the instrument. The HSI needle would disappear, and a clear red or black flag would appear, warning the pilot that the data couldn't be trusted. That system worked when it worked. But in the 1970s, something unsettling came to light. Certain nav radios, specifically the Collins 51RV-2B series, had a critical flaw. If the output signal from the nav receiver was interrupted due to a short circuit or broken wire, the instrument might still show perfect alignment, even when no valid signal was being received. It created what pilots fear most, a false sense of accuracy. The problem had been documented as early as 1975. The recommended fix was to upgrade all 108 variant Collins receivers to the newer 109 variant, which eliminated the fault. Some airlines complied, others didn't. The issue wasn't enforced. It was only a recommendation. Then, in 1984, McDonnell Douglas issued a technical bulletin to operators, warning of the risk of frozen glide slope or localizer indications. They referenced several models, but notably, they did not include the Collins 108 variant units in that warning. Why? Because they assumed, after the 1975 memo, that everyone had already upgraded them. But not every operator had. And so, in the cockpit of this aging DC-9, now flying its third leg of the day, there may have been one of these unmodified legacy nav receivers still quietly installed, sending what looked like perfect data, but with no validation behind it. The instruments could be showing a centered localizer or glide slope, while in reality, the aircraft was drifting dangerously off course. For the pilots, there was no fail flag, no warning, just calm, steady needles. And that's the deadliest illusion of all. By 1985, the dangers of frozen instrument indications had become more widely recognized in the aviation community. During a safety seminar held in the United States that year, the issue was directly addressed, and notably, pilots from Alitalia were in attendance. But somewhere between the briefing room and the cockpit, the message didn't fully land. The hazard never made it into standard training materials. Line pilots, the ones actually flying the aircraft, were largely unaware of the lurking danger. Normally, approaches on the DC-9 were flown with the nav switching unit set to approach mode. In that configuration, the captain's instruments would receive data from nav-1, while the first officer's instruments would rely on nav-2. This separation allowed a comparator system to monitor both signal paths. If a discrepancy arose between the two sets of readings, it would trigger a warning, a system designed to catch failures before they became fatal. It gave pilots a second layer of assurance, and that assurance is exactly why the risk was considered manageable, at least in theory. Now, let's return to the aircraft itself. Once the DC-9 arrived back at Stand 16 in Milan, the captain contacted maintenance. The navigation failure had returned. Only now it had flipped sides, just as expected. The engineers responded by removing both nav receivers. In their place, they installed a King KNR 6230 in the nav-1 slot and a Collins 51RV-2B in nav-2. But here's the critical part. Both units were of the non-monitored type. They did not guarantee a fail flag when something went wrong. And the flight crew? They had no idea. After the swap, standard procedure required the maintenance team to perform a test. The two nav receivers were checked against the nearby auto VOR and auto localizer. The results? Normal. But due to the location of the stand, they couldn't test the reception of the ILS glide slope, the vertical path that guides the aircraft safely down to the runway threshold. Without a full systems check, the aircraft was cleared to fly. A note was entered into the tech log instructing the pilots to conduct an automatic approach at their destination, Zurich, to restore the aircraft's CAT-3 autoland capability. That requirement took on greater urgency, as fog was now forecast to develop at the end of the fourth flight. Autoland might become essential. The pilots acknowledged the note and carried on with their preparations. The first officer would be the pilot flying for the next leg to Zurich. While he reviewed departure procedures, passengers began boarding. There were 40 of them, plus the 6 crew, 46 souls in total, when Alitalia Flight 404 taxied out to runway 36R. At 1836 local time, the DC-9 began its takeoff roll. The first officer advanced the throttles into takeoff thrust. The engines roared to life, and the aircraft surged down the runway with typical McDonnell Douglas power. Takeoff was smooth, the climb uneventful. There were no signs of any issues with the navigation system. As the aircraft ascended into the darkening alpine sky, it leveled off at flight level 200, 20,000 feet, just high enough to clear the snow-covered peaks that separated Milan from Zurich. But this wasn't a long cruise. Less than 2 minutes after leveling off, the captain began tuning the VHF to listen for the Zurich ATIS and pick up the latest weather report. Surface winds in Zurich were reported at 240 degrees at 8 knots, a tailwind for their intended runway, 14. The captain began considering a circling approach to runway 28 instead, which would require maneuvering the aircraft visually after breaking out of the clouds, complex and inherently riskier. A few minutes later, updated ATIS information confirmed that runway 14 was still in use. Despite this, the cockpit voice recorder later captured the captain insisting on briefing for the circling approach. It was a long, detailed explanation. Some would say overly complicated for a flight this short. Now, in theory, it's good to mentally prepare for all possibilities. But a circling approach at night, in marginal weather, with fog forming and unfamiliar terrain, this wasn't something to take lightly. The more complicated the briefing, the easier it is for key elements to get lost. In aviation, approach briefings are meant to crystallize the mental picture of what's coming, not cloud it. There was also another undercurrent developing inside the cockpit, one that would become critical. All conversation was in Italian, but translated transcripts revealed a pronounced authority gradient. The captain had adopted a teaching tone, speaking to the first officer more like an instructor than a colleague. That might have seemed normal in the 1990s, especially in hierarchical cultures. But in high-pressure environments, it can be dangerous. Why? Because when the time comes to speak up, to challenge a decision, question an assumption, or report a subtle inconsistency, the more junior crew member might stay silent. And when seconds matter, silence can be fatal. To be fair, the captain's instructional tone may not have come out of nowhere. As the first officer continued his approach briefing, it became clear something was off. He was referencing the wrong approach plate, mistaking runway 16 for runway 14. He read out the outer marker crossing altitude for the incorrect runway, and the captain didn't immediately correct him. That small slip set the tone for what followed. Instead of tightening their focus on the approach they were actually flying, the crew drifted into a lengthy discussion about procedures in the event of radio communication loss. On a flight this short, that's not an efficient use of time. What they really needed to do was verify the intercept altitude and distance for the glide slope. That, and cross-check the correct outer marker altitude, something fundamental to safe instrument landings. In most cases, flying an ILS is straightforward. The HSI and flight director guide the pilots down, showing both lateral and vertical deviation. If all indications are normal, and you're at the right place at the right time, things usually go smoothly. But there have been rare, but very real, cases of false glide slopes being captured, particularly at the outer edges of the signal cone. To guard against that, pilots are trained to verify their position before intercepting. The simplest method is to confirm you're at the correct altitude and distance when the glide slope becomes alive. After that, the vertical descent rate should remain steady, typically between 700 and 900 feet per minute. If it's outside that range, it's a red flag. Cross-checking the aircraft's altitude at the outer marker, or an equivalent DME distance, is another safeguard. But here, another subtle issue crept in, one that had plagued this aircraft's cockpit for years. The DC-9 was fitted with a type of altimeter that displayed hundreds of feet using a rotating needle, and thousands of feet using a small inner drum. On paper, the system made sense. But in practice, it was clumsy. Reading the altimeter required 2 separate visual scans, and the tiny drum made it especially easy to misread altitude, particularly under stress, in low light, or with cognitive overload. This altimeter design had already been flagged in earlier reports for contributing to altitude misinterpretations. And now, with descent underway, that same risk returned. As the aircraft passed through controlled airspace, Zurich approach came on frequency. The controller asked their heading. The crew replied, 350 degrees. They were told to adjust slightly, 340 degrees, a minor correction. Clearance was given to descend to flight level 140. During descent, the captain tuned into the updated ATIS broadcast. Information echo. Runway 14 was still active. Winds were reported from 250 degrees at 7 knots. Visibility, 10 kilometers in mist. Cloud layers scattered between 1,500 and 4,000 feet. By all accounts, decent weather for a precision approach. Yet the crew continued debating the arrival plan in detail. Perhaps too much detail. They were handed off to the approach controller, who instructed further descent to flight level 100. At around 1900 local time, the first officer brought up the request from maintenance. Should they perform a Category 2 approach to validate the aircraft's autoland system? The captain agreed. Testing the Cat 2 system would be necessary to restore Category 3 certification, which they might need on the foggy return leg. But oddly, that decision was made with little discussion about the procedures involved. No review of additional callouts. No confirmation of which autopilot modes would be used. No role assignments. The only thing clearly established were the minimums, the decision altitude for the approach. That silence spoke volumes. Cat 2 approaches are demanding. They come with strict procedural requirements, heightened callouts, cross-verifications, and readiness to go around at the slightest deviation. But instead of diving into that, the crew continued chatting about low-probability failures and loss of comms procedures, subjects far less relevant at this point in the flight. From the outside, the crew appeared professional. They weren't joking or distracted. They weren't reckless, but their focus was scattered, and they weren't following their standard operating procedures as tightly as they should have. And then came another clue, one that should have reset the entire mental picture. The first officer suddenly realized he had been looking at the wrong approach chart the entire time. His minimums didn't match the captain's. A quiet moment passed, then a deeper issue emerged. The missed approach procedure he had briefed was for the wrong runway. The captain hadn't caught the mistake either. He had misunderstood. In aviation, the threat isn't always a dramatic system failure. Sometimes it's small cracks, little mismatches, unchecked assumptions, misreadings, that slowly accumulate. And by the time you notice them, you've already passed the point of no return. In commercial aviation, briefings during descent are generally avoided when possible. The reason is simple. Descending into busy airspace, often surrounded by complex terrain and multiple radio instructions, is not the time to divide attention. But on short flights, it's sometimes unavoidable. When it must be done, it should be clear, concise, and accurate. This briefing wasn't. Zurich approach cleared the aircraft to turn left to heading 325. Radar vectors for the ILS approach to runway 14. They were also told to descend to flight level 90. 2 minutes later, as they passed abeam the airport, the captain remarked, "We're passing abeam Cloten at FL 90. We're being kept high." That comment offers a revealing glimpse into the captain's situational awareness. In truth, they hadn't been told how many track miles to expect on vectors. Without that, judging whether they were high or low was speculative. But the captain perceived they were high, and that perception likely shaped every decision that followed. As the aircraft descended through FL 100, the first officer reduced speed to 250 knots per regulations. But the captain urged him to slow even further, warning that excessive speed would carry them too far from the airport. His tone was once again instructional. This was no training flight, but it was starting to feel like one. Soon after, approach requested they reduce speed to 210 knots and descend further to flight level 60. The airspace was congested. Multiple aircraft were being vectored simultaneously, and the controller was managing spacing carefully. The crew complied. A brief exchange followed about anti-ice settings, which they decided were not required. Then the captain brought up something that would soon prove critical. He mentioned that the outer marker for the approach was at 1,200 feet, and that it could be identified at 3.8 nautical miles from Cloten VOR. But that wasn't entirely accurate. The correct crossing height was 1,148 feet QFE, altitude above airfield elevation, not rounded down. And the distance was from the ILS DME, not from the Cloten VOR. The captain had likely rounded the figure and referenced the wrong navigation source. He may have been attempting to double-check the approach chart after the earlier confusion with the first officer's incorrect briefing. If so, he was cross-verifying. But his numbers were off, and this seemingly minor detail would matter. At Alitalia, standard practice at the time was for the pilot monitoring, in this case, the captain, to set his altimeter to QFE, which reads altitude above the airfield. Meanwhile, the pilot flying would remain on QNH, altitude above sea level, until final approach, when both would switch to QFE. It was a cumbersome system, and it opened the door to error. Today, most airlines use QNH throughout the approach to avoid exactly this kind of confusion. 2 minutes later, the approach controller instructed a right turn to 070 degrees. The captain read back the heading. They were now on a base leg, moments away from intercepting the localizer. About a minute later, they were cleared to descend to 4,000 feet, then turn right to heading 110, cleared for the ILS runway 14 approach. And now, everything began to unravel. According to the published procedure, 4,000 feet was the altitude to be maintained until 8 DME, 8 nautical miles from the ILS antenna, where the glide slope could be safely intercepted. That's where the descent should begin. But the autopilot on the DC-9 had a quirk. When set to approach mode, and when it sensed an ILS glide slope signal, it would begin a shallow descent, 700 feet per minute for 10 seconds, before fully coupling with the glide slope. If the glide slope signal was false, or if it was captured too early, the aircraft would begin descending anyway, regardless of position. And in this case, that's exactly what happened. Here's how the radios were set up. The first officer, flying the aircraft, had tuned NAV-2 to the Cloten VOR with a course of 138 degrees, preparing for a possible missed approach. The captain, monitoring, had tuned NAV-1 to the ILS frequency, also with a course of 138 degrees, aligned with the inbound approach. Remember that NAV switching unit? When set to approach, it automatically copied the ILS frequency from NAV-1 to NAV-2, but NAV-2 still displayed the VOR frequency for reference. Critically, DME-2 would also read distance from the VOR, not from the ILS. So while the pilots believed they were both monitoring ILS signals, they were receiving different distance readouts and possibly different glide slope behaviors. The comparator was active, designed to warn if a discrepancy arose between the captain's and first officer's instruments. But inside NAV Receiver 1, something had gone wrong. We'll never know exactly what. Perhaps a short circuit or a signal dropout. But for some reason, the receiver began sending a null glide slope signal, a value that, due to the receiver's analog design, mimicked a valid centered signal. That's the deadly flaw. Because this particular model of receiver, like others we mentioned earlier, did not trigger a fail flag when it lost signal. The glide slope needle on the captain's side looked perfectly centered. The aircraft began descending, gently, as designed, and the pilots, trusting their instruments, had no idea they were sliding below the glide path. Too early, too low, too soon. The localizer was working fine. The aircraft was on the correct horizontal path, but the vertical information was an illusion. And with mountains rising in the darkness ahead, that illusion would soon become irreversible. The aircraft was now closing in on the localizer centerline. On the captain's instruments, the glide slope appeared perfectly centered. No flags, no warnings. Just a quiet indication that all was well. But it wasn't. On the first officer's side, things looked different. His nav receiver had no faults. It correctly showed that the aircraft was still too far from the glide slope. His glide slope indicator remained parked at the top of the display, out of view, because the aircraft hadn't reached the proper intercept point yet. But remember what the captain had said earlier? That they were being held high? That belief was still quietly influencing his judgment. So when he looked at his HSI and saw a centered glide slope, it reinforced what he wanted to believe, that they were now on the correct descent path. Even though the DME still showed more than 12 miles, well beyond the normal 8-mile intercept point, he trusted the indication in front of him. At the same time, the flight mode annunciator showed NL arm, indicating that the flight director selector was in normal mode. As the glide slope discrepancy became apparent, the comparator warning light illuminated, detecting the mismatch between the captain's and first officer's HSIs. That's when the first officer asked, do you have the glide? The captain responded, on 1, referring to his NAV-1 receiver. 5 seconds later, the first officer replied, I don't have it. That should have been the turning point. Instead, the captain doubled down. Good. Let's do it on 1, he said. Those words, so ordinary, so subtle, were the final alignment in the Swiss cheese model. Every hole, every missed check, every flawed assumption now fell into place. The first officer, despite having previously seen that NAV-1 was suspect, agreed. He switched the nav mode from approach to radio 1. Instantly, all 4 navigation instruments, the HSIs and ADIs on both sides, began sourcing data solely from the faulty NAV-1 receiver. That's when the glide slope magically appeared on his side too. And the comparator warning, gone. To an outside observer, this system design seems deeply flawed. Why allow a single faulty receiver to feed every instrument in the cockpit without fail flags? The logic was probably that approaches should always be flown in approach mode, where redundancy and cross-checking exist. But in this moment of confusion, the crew made a knee-jerk decision, a shortcut that masked the problem instead of solving it. It looked fixed, but the danger had just been multiplied. The first officer called for flaps 15 and armed the ILS mode on the autopilot. The system reacted immediately. It reduced the descent rate from 150 feet per minute, previously set in vertical speed mode, to 700 feet per minute, in line with glide slope capture logic. At the same time, the autopilot captured the localizer after a minor overshoot to the left. But there was a fatal problem. The aircraft was already 1/500 feet below where it should have been to intercept the glide slope. This was a gross vertical deviation, one that should have triggered immediate alarm. The crew could have cross-checked the DME, which still read over 12 nautical miles. The glide slope intercept point was at 8, but no one looked. Or if they did, they didn't speak up. And this is where we need to pause. In aviation, strange instrument behavior demands one thing above all else: curiosity. When things don't add up, when flags don't match indications, or a system behaves differently than expected, the first response must be, why? The best practice is clear. The pilot flying focuses on keeping the aircraft stable and safe. Meanwhile, the pilot monitoring announces the issue and begins a methodical scan of all indications, seeking patterns, cross-checking sources, and reviewing checklists. That process might require abandoning the approach. It might mean requesting delaying vectors or entering a holding pattern. But it's always the right move when something doesn't feel right. Here, a short delay could have saved everything. The captain might have compared his glide slope reading with the first officer's. He could have checked the DME against the expected intercept distance. Together, they may have realized that NAV-1 was feeding them a lie. Instead, they descended, trusting a signal that never should have been believed, and the terrain that lay quietly in the shadows below waited for no one. Given the recent work done on the aircraft's navigation radios, a cautious approach would have been to continue the descent using the first officer's instruments, the ones still showing accurate readings. With careful cross-checking between altitude and DME distance, they could have stayed safe. A Category 2 approach would have been off the table due to the instrument fault, but that possibility was never even discussed. Instead, the crew committed. Flaps 15 were selected. The captain calmly announced, "Localizer capture, glide path capture. So we are on the beam, a little bit off track." He was referring to a small lateral overshoot, nothing major. From their perspective, the aircraft was now established perfectly on the ILS. The first officer set QFE 970 HPA on his altimeter and called it out. Moments later, the aircraft descended through 3,700 feet, triggering an altitude alert. The MCP mode control panel was still set at 4,000. The captain responded, I cancel, then reset the MCP to 5,000 feet, the go-around altitude. That too is telling. All their actions showed one thing. The crew fully believed they were flying a valid ILS approach. The localizer was real. The glide slope looked real. Their belief, already solidified, was now being reinforced by every cue they chose to trust. This is confirmation bias in its most dangerous form. Faced with conflicting data earlier, like the comparator warning, they had made a decision to trust the false signal. And now, every piece of correct information that contradicted their understanding was mentally filtered out. They didn't question why they were still far from the runway at such a low altitude. They didn't revisit the fact that the glide slope came alive far too early. They just flew. And they were flying 200 feet below the real glide slope. This would have been survivable, if not for what came next. The terrain around Zurich is deceptively high. About 5 miles out on final for runway 14, a modest mountain named Stadlerberg rises from the landscape. On a standard glide slope, it's a non-issue. But if an aircraft descends below profile, Stadlerberg becomes a threat. Two critical dangers now emerged. First, the terrain can block the ILS DME signal, making altitude-distance crosschecks impossible. Second, and more dangerously, comes the black hole effect. In darkness, with no city lights or visual references on the hill, the mountain becomes invisible. A featureless void. Pilots descending into it can't see that anything is wrong, until it's far too late. And Stadlerberg had no obstacle lights at the time, just a silent, black shadow, standing in their path. Now here's the tragic twist. The official AIP charts for Zurich clearly marked the terrain. But Alitalia was using a simplified version, where the profile view of terrain had been removed. The hill wasn't even visible on the charts they had in front of them. Around the time the captain reset the altitude to 5,000 feet, the landing gear was likely extended. There was no specific gear call-out, but when the first officer called for flaps 25, no warning horn sounded, meaning the gear had already been selected down. If it hadn't, the system would have screamed. That timing matches the captain's next concern, spacing. He instructed the first officer to reduce speed, worried they were closing in on the traffic ahead. Then he called out, "Outer marker check, 250 feet." That was correct, but at the time, they were already descending through 1,600 feet, still more than 4 miles from the actual outer marker. If that didn't raise alarm bells, nothing would. You might ask, where was air traffic control in all of this? It's a fair question. Normally, an approach controller would confirm that the aircraft is established on the ILS. But at the time, there was no formal requirement for controllers to monitor altitude once cleared for approach. Nor did pilots need to report they were established unless prompted. In this case, the crew never confirmed it, and the controller never asked. There was also no low-altitude warning system installed in the Zurich Tower, something that has since become standard at most major airports. So now, the aircraft was descending, off the glide slope, into high terrain, in total darkness. And the only thing left standing between them and disaster was one final safeguard: the Ground Proximity Warning System, GPWS. But we'll get to that next, because even the best warning systems depend on one thing above all else: a crew willing to act when the moment arrives. The autopilot continued its descent at 700 feet per minute, quietly following the logic it was programmed for. The first officer called for flaps 50, their final landing configuration, and the captain set them. At this point, they passed 8 nautical miles from the runway, precisely where they should have begun descending from 4,000 feet, or roughly 2,600 feet with their QFE altimeter setting. But instead of being on profile, they were already down to 1,100 feet. That's when the first signs of doubt began to surface. The captain remarked that it was about 3.8 miles to the outer marker. At that distance, they should have been at least 150 feet higher. Something wasn't right. The first officer asked if they had already passed the outer marker. He asked again moments later. He was clearly confused by what he was seeing. The captain responded, No, it hasn't changed yet." His answer was vague, perhaps referring to the marker light or DME reading, but it didn't clarify anything. He followed up by noting they were still at 7 miles, as if trying to convince himself the math still worked. But it didn't. The instruments still looked fine. At least the ILS indications did. That illusion held the crew's situational awareness in a tight grip. Just as the captain might have started processing the inconsistency, a radio call came through. The approach controller instructed them to reduce speed at their discretion and switch to tower frequency. It was a routine handoff, but it disrupted the captain's focus, just as his doubts were beginning to form. By now, they were below 1,000 feet, still far outside the outer marker, and flying straight toward the unlit slope of Stadlerberg. The hill was invisible in the darkness, and although the weather was decent, they were likely in low-level clouds drifting off the terrain. From their perspective, the approach lights were completely hidden behind the mountain. You might expect the ground proximity warning system to activate at this point. But this aircraft was fitted with an older version of GPWS. It didn't have terrain mapping or predictive features like modern systems. It only reacted to certain inputs, and none of them triggered. The gear was down. The flaps were set for landing. Mode 1, which monitors excessive descent rates, didn't go off because they were within normal range. Mode 2, which detects rapid terrain closure, wasn't triggered either because the slope ahead hadn't yet produced a sudden closure rate. And Mode 5, which alerts for glide slope deviation, didn't activate because the aircraft still believed it was perfectly on the glide. Every technical safety net had failed. Only one safeguard remained: the pilots. And at last, their instincts started catching up to the situation. At 19:10 and 56 seconds, the captain said, "That doesn't make sense to me." The first officer replied, "Nor to me." A second later, the captain shouted, "Pull, pull, pull!" And the sound of the autopilot disengaging was recorded on the cockpit voice recorder. For a moment, it sounded like they were taking action, but it likely wasn't a full go-around. The captain may have misread his altimeter. The display used a small drum for thousands of feet and a needle for hundreds. He may have seen 300 feet and mistaken the drum as reading above 1,000. That would place them at 1,300 feet in his mind, high enough to level off temporarily. But the aircraft was actually only 350 feet above terrain. The radio altimeter could have revealed the truth, but no one checked. Then came the final action. As the aircraft crossed about 6 miles from the runway, the first officer called it. Firm, final, and decisive. Go around. But by then, the mountain was already in front of them. The first officer had already started the go-around. He advanced the thrust levers and pitched the aircraft nose up to about 5.4 degrees. Later analysis showed that if this maneuver had continued, they would have narrowly cleared the top of Stadlerberg. The mountain would have been behind them, not in front. But the captain intervened. Still trusting the false glide slope indication on his instrument panel, still believing they were just a little low, he called out, "No, no, 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 no! Catch the glide!" The first officer, possibly caught in the grip of cockpit authority and deference, complied. He lowered the nose. Seconds later, The captain asked, "Can you hold it?" The first officer replied, "Yes." Then came the radio altimeter alert. They were now just 200 feet above the ground. The last words captured on the cockpit voice recorder were the captain saying, "Hold on, let's try." At 19:11:19, the aircraft slammed into the northern slope of Stadlerberg. The impact tore the DC-9 apart. The wreckage ignited instantly. All 46 souls on board were lost. There had been no mayday, no radio call, nothing to warn the world what was happening. Zurich's air traffic controllers, unaware of the crash, continued clearing other flights for arrival. It wasn't until another inbound aircraft reported a fire on the approach path that the truth became horrifyingly clear. The airport shut down immediately. Emergency crews rushed to the scene. But when they reached the wreckage, it was already over. The investigation began at once. It didn't take long to uncover the chain of failures. A false glide slope indication from nav receiver 1. A likely misread altimeter by the captain. The crew's failure to recognize the instrument fault. Inadequate analysis when the comparator warning lit up. A departure from standard approach procedures. Poor cockpit communication and coordination. But the final, fatal link, the one that sealed the fate of everyone on board, was the captain's decision to override the first officer's go-around. The report led to sweeping recommendations. Nav systems without proper failure detection were to be banned. The unreliable drum pointer altimeters were once again highlighted as prone to misreading. 13 additional findings addressed ATC practices and the need for clearer, terrain-aware approach charts. But one lesson rose above all others. If a go-around is initiated by either pilot, it must be completed, without hesitation, without argument, without delay. That single principle has echoed through flight decks around the world ever since. Because in the sky, when you doubt what you see, you go around, and you live to fly another day.